Hello, this is part 4 of the causal graphs tutorial on causal axioms and the sort of dark magic of causal graphs. What I'm going to try and suggest is that causal graphs gives us a way of knowing more information than we initially thought we could work out. And the analogy is kind of with geometry. So in high school you may have been given these tests in mathematics. So you have some lines, parallel lines, you know some of the angles, and you have to work out what these other angles would be. And to begin with, it seems very hard to tell what the angle G would be, or the angle C. But you know that there are a set of geometric axioms. So for example, you know that there are a certain number of degrees in a triangle. You know that parallel lines have similar degrees between them. And a geometric calculus for putting those together. And actually you can solve all of these problems. You can know the angles of all of these things just by putting those things together. So how can we apply this to causal graphs, especially when sometimes we can't measure some of the things that we want to make statements about? So Judea Pearl and his colleagues have put together a set of causal axioms. So it's a calculus that aims to exchange probabilities based on intervention, kind of experiment intervening on something, this do calculus. Take those things and express them in terms of probabilities based on things we can observe. So this would be really helpful. It would mean that we can make statements about causality just based on observations rather than having to do experiments directly. There are 3 rules that I'm going to go over. They're expressed in probabilities like this, but hopefully they are to some extent intuitive. So I'm going to try and explain them with this example of detecting when an alarm goes off. Let's say it's this as kind of smoke alarm. And we think this is how the world works. If there's a fire, the fire causes smoke, and the smoke causes the alarm to go off. The alarm also has a button, and you can hit the button, and that will also cause the alarm to go off. And the first rule, it says that we can delete some observations. So things that are not relevant to something we're trying to work out can be ignored. So for example, if we're interested in, excuse me, smoke in here. If you're interested in the probability of the alarm going off, the probability of hearing alarm, given that we intervene and hit the button, and given whether there's smoke or not, and given whether there's fire or not, well, this probability, the percentage that this works out to be, should be the same as this statement. So it should be the probability of the alarm going off should be just the probability of hitting the button and the probability of smoke. Because in our world there's no direct link between fire and the alarm, we don't need to know about this. This shouldn't affect the probability in any meaningful way. In other words, smoke blocks all the paths from fire to alarm. So that's deleting observations. Some observations we can delete. Rule 2 is that sometimes we can exchange probabilities based on interventions for probabilities based on observations. So let's imagine that we're in this world where a fire or cigar smoke can cause smoke, and that will set the alarm to go off. Now, the probability that we intervene and introduce, we sort of do an experiment and cause a cigar to be lit, should be the same as just the observational probabilities. And that's because there's no backdoor path from cigar to alarm. In another way of thinking about this is that cigar is already randomized. According to this world, there's nothing that influences whether a cigar is there or not that relates to the rest of our system. So this is already a kind of experiment. We've already removed any confounding nodes, any confounding arrows going into cigar. So we can just rely on the observations instead. Now that would be different if there was a system like this. So let's say that there were a group of evil cowboys who went around starting fires and smoking cigars. In this case, we can't claim that these two things would be different because there's a backdoor path from cigar to alarm. We need to control for this. So we need to control for evil cowboys, remove this causal arrow, or remove this causal arrow. Or control for fire, I suppose, that would also work. So again, this is the point. There is a confound now introduced by this evil cowboy. And that means that the probability of running an experiment is different from the probability of observations. We can't apply the second rule in this case. The third rule says that we can delete some interventions. So let's say that fire causes smoke. Smoke causes the alarm to go off, but it also causes damage to the furniture, smoke damage or something. Now, the probability of the alarm going off, given that we intervene and we damage the furniture, should just be the same as the probability of observing that the alarm is going off. And that's because, as far as we know, there's no causal effect from damaging the furniture that will make the alarm go off. So we can sort of ignore or delete this intervention. So those three rules should be reasonably intuitive in the sense that we can make statements about the probabilities based on just common sense, basically. But it turns out, if you combine these together, you can figure out things that you didn't think you could figure out before. So let's say that you're interested in the effect of fire making the alarm go off, but you think there may be electrical faults in the building that you don't know about necessarily. And those might cause fires themselves, and they might also cause the alarm to go off by some sort of malfunction. So now there's a backdoor path here, and we can't measure whether there are electrical faults. Can we make some statement about the influence of fire on the alarm going off? And it turns out you can. You can combine these things to turn a statement of based on intervening on fire, so actually setting a fire, and express them in terms of the probabilities of observation. I'm going to try and demonstrate how you can do this. So if you're interested, so these axioms are complete, so you can discover a solution if one exists. And there are algorithms that help you discover these in reasonable times. And actually the DEPT tool has implementations of some of these. If there isn't a solution, then you have to do an experiment. And this is also useful information. And algorithms tell us, algorithms exist to tell us what variables to experiment on, or to discover other variables to manipulate if we can't manipulate the target. And again, that's what DEPT does for us. So these are a set of useful axioms. All right, black magic, how does it work? The first thing is backdoor adjustment. So let's say that we're interested in measuring the effect of going on walks outside on making you happy. But you think there may be a confound. So we've observed lots of, we put out a survey, do you go on walks, are you happy or not? But there might be a confounding variable. Some people own dogs which make them take walks, and the dogs might make them happy independently. So there are these two causal arrows. We can't force people to go for walks. We've only got a survey in our little experiment. So how can we calculate the effect of walking on happiness? So it turns out you can apply some of the rules to turn the probabilities of intervention into probabilities of observation. An intuitive way of thinking about this is the following. So the probability of being happy if you were to force someone to go for a walk, probability of them being happy if you were to force them to go for a walk, turns out to be the probability of being happy if you walk and if you have a dog multiplied by the probability of having a dog, plus the ability to, the probability of being happy if you walk and you don't have a dog, weighted by the probability of not having a dog. So everything in this formula is about observational probabilities, and it follows from the axioms. And actually this is reasonably conceptually close to statistically controlling for whether you have a dog or not. The second type of adjustment is front door adjustment, and this is the real kind of black magic for me. So at this time we have a sort of similar setup, but now we can't observe one of the variables. So let's say smoking causes tar to build up in the lungs, and tar gives you cancer. Some people argue that there might be a gene that makes you want to smoke more, and a gene that also makes you more susceptible to cancer. So the effect of smoking on cancer is confounded by a possible genetic effect. There's a backdoor path here from smoking to cancer. How can we control for the smoking gene when we don't know what it is? It's just a sort of hypothetical, can't measure it. Well, let's try and estimate each link in the causal chain that we're interested in turn. So the first link that we're interested in is the effect of smoking on tar. We would like to measure this. We can observe whether people smoke and whether there's tar in their lungs, let's say. But there's a backdoor path here that confounds this. So here's an arrow going into our first variable, and here's a non-causal path around to tar. However, there is a collider. So smoking and tar and cancer cause a collider here. So this backdoor path is already blocked. So we can just use the observed probabilities. So we can work out the average causal effect of smoking on the buildup of tar. So we call it E1. Now we have to work out the effect of tar on cancer. And hopefully you can see some similar problem here. In this case, here's an arrow going into our first variable, and here's a non-causal path around to cancer. So the smoking gene is confounding this. However, we can block this non-causal path by controlling for smoking. So if we control for smoking, condition on smoking, then this backdoor path is blocked. The correlation can't flow around, so anything that we observe should be the causal path. And that gives us the second average causal effect here. So now we know the causal effect of the first step, causal effect of the second step, and there's a way of combining these to figure out the total effect of smoking on cancer. even when we can't measure confounding variables. So that's a really powerful conclusion to come to, and it requires a lot of explaining, and it does seem a bit like black magic. But if you believe the causal axioms, and you believe this is a reasonable model of the world, then you can make statements about causality based on probabilities derived from observing things. So far, we've been thinking about cases where we might have loads of data and sort of ideal situations where we can work out probabilities effectively. With real data, that's not always the case. So in the next little video, I'm going to talk about how we might use these things with real data. Thanks.